Artificial intelligence offers incredible opportunities to explore cognition and the mind. In this project, I use artificial neural networks, or ANNs, to simulate basic cognitive behaviors. My research draws inspiration from Max Bennett's 2021 paper entitled Five Breakthroughs, a First Approximation of Brain Evolution from Early Bilaterians to Humans. Specifically, I focused on the second breakthrough, reinforcement in early vertebrates. This work seeks to illustrate how reinforcement mechanisms shape adaptive behavior. My name is Stephen Deem, and this presentation highlights the results of my study on the emergence of cognitive behaviors in AI. The second breakthrough in Bennett's work emphasizes how early vertebrates adapted to their environments using reinforcement learning. To replicate this, I created a virtual environment that could dynamically change. Within this environment, I implemented an AI framework with 6 sensory inputs, 6 behaviors, and an ANN. The ANN processes sensory data and selects behaviors. To simulate evolution, I designed an algorithm that evaluates fitness through 2 criteria, namely the amount of progeny that an AI has, and secondly, the number of actions that it takes. After each simulation, the algorithm prunes 80% of the agents, retaining only the fittest to reproduce and adapt. This setup enabled me to rapidly test multiple generations of AI and observe emergent behavioral changes under varying environmental conditions. The results demonstrated clear adaptations through reinforcement learning. By the 10th generation, the ANN consistently optimized behavior for the given environment. 2 experimental patterns stood out. In experiment 1, a dominant behavior emerged alongside secondary behaviors that maintained some presence, showing diversity. Experiment 3, however, exhibited a sharply dominant behavior with other behaviors varying over time. These experiments highlighted the flexibility of model-free reinforcement learning, where behaviors emerged purely from reinforcement and environmental feedback without explicit programming. The charts that are in the middle of this page show the prevalence of the selection of the 6 behaviors over 20 simulation runs. Each simulation comprised thousands of individual artificial intelligences, each selecting the behaviors according to the sensory inputs in their artificial neural network. This project serves as a compelling proof of concept for studying adaptive cognitive behaviors using artificial neural networks. For this study, I attempted to demonstrate how reinforcement learning can drive behavioral adaptation in response to environmental pressures. Despite the relatively simple structure of the ANN and the limited scope of the virtual environment, the results clearly illustrate the emergence of behaviors that optimize survival and reproduction. The significance of this study lies in its ability to showcase the power of reinforcement learning as a foundational mechanism for cognition. By simulating the evolution of thousands of agents over multiple generations, the experiment revealed how environmental pressures lead to the selection of advantageous strategies. These findings mirror the principles of natural selection in biological systems and highlight how similar dynamics can be applied in artificial settings. Looking ahead, this framework has potential for deeper exploration. Starting at the first breakthrough that Max Bennett identified, steering, we could expand the study of cognitive evolution. Additionally, evolving not just behaviors, but also the ANN architecture itself would allow exploration of more advanced cognitive phenomena and emergent behaviors.